Greetings to all of you. Welcome back. We have started kinematics, and today we are going to discuss the equations of motion and their derivation, and what does the mean of what is the physical meaning of our equations. So, equations of motion is the title of today's video. So, before diving into our calculations and different kind of expressions, one must know that what does it mean by equations of motion. So the major contributions in the kinematics were made by Galileo, and before Galileo, from Plato to Galileo, it was considered that all the phenomena, all the equations were for the celestial bodies, the bodies outside this world, or outside the Earth's surface. This is because that Earth's particles are so imperfect, and we cannot evaluate such expressions that we used for the celestial bodies. There are a lot of the work in astrophysics. Kepler laws have been discovered, and different kind of theories and equations were there, but this was the first attempt to discuss the motion in Earth's atmosphere. So before that, it was considered that all those laws and all those equations withholds only to celestial bodies, but these equations of motion were the first step toward the analogy, and these says that all these equations are also workable in our atmosphere in this frame of reference, but we have too much of the constraints, or too much of the conditions that we have to take care of, like the air resistance or the shape symmetry or other kind of things. So they are as well as, but if we idealize all the situations, as we remove all the air resistance, and we take the ideals of air exist and other kind of equations, other kind of the conditions, then these equations of motion are fair enough to discuss any kind of motion. So here we have four major equations which deal with all kind of motions, but here is also a constraint that all of these equations that we are going to write and we are going to derive are for, let me say, uniform acceleration. So what does it mean by uniform acceleration? This is a very valid point, and this is worth remembering, that you as a physicist must know that all the equations of motions are for uniform acceleration. So what does it mean by uniform acceleration? So acceleration, as we have defined, that it is a change in the velocity by the time. So change in the velocity, how it can be uniform if acceleration is the change in the velocity. So let's suppose we have a car, and a car start traveling from 0 and gain the speed of 3 meter per second, let me say, and in the next interval its velocity increase by 6 meter of second, then by 9 meter per second, then 12 meter per second. Then if you calculate the difference between the frequencies, difference between the velocities, you will get the same acceleration. So this is the case. There is another case of a free fall motion, in which the gravitational acceleration holds in Earth's atmosphere or near the surface of meter per second square. This is the gravitation. So these are the uniform cases, uniform acceleration cases. So what were these equations and how we can derive them? So here we have some of the expressions, and it is more promising to remember the relation in the place of other kind of the numbering, that first equation, second equation. You must know about the relation, that from what these are derived. So the first one is the relation between displacement and average velocity. So far we have discussed that our average velocity, this bar represents the average, is the sum of the velocities. So this is the average velocity expression, but by the definition we know that velocity is the displacement over time. So if we put both of them and put the formula for the displacement also over t is equal to v naught plus v over 2. Here v naught is let me say that initial kind of position, or the velocity, or final. One of them is the naught kind of thing, and other is the smooth v or x. So if we evaluate this t will get multiplied here, and we ended up with our first relation. So this is the first equation of motion, and it is derived by displacement average velocity relation. Then we have the negative term, which is the velocity and time relation. So velocity time relation, we know that by definition acceleration is the change in the velocities by the time. So if we multiply this t here, we get where is it, at is equal to v minus v naught, and we get derived this equation that v is equal to v naught plus at. So this is the second relation of the equation of motion, which is derived from velocity times graph. The third relation is of position and time. So as we again elaborate the average velocity case, so it is the displacement over time, and if we put the expressions for that, we will get to know that this is the x minus x naught over t. So x minus x naught will be equal to this one. Then we put the expression for the average velocity by t and x minus x naught, and this might be regarded as s, or the distance traveled. So here we have v, and by v naught, by the last relation that we deduced, here is that. So we will put it here. So we will have, let me say, v naught plus at by this 2, and this t get multiplied as well. So this will be 2v plus at by 2. v3 plus half at square. This is the third relation, and the fourth one is of velocity and displacement relation. So velocity, the relation between velocity and displacement, as we have discussed earlier, is that the change in displacement is equal to the average of the velocity, and we will start from this term. So this is v plus v naught by 2 times the t, and if we put in the expression here for t, v plus v naught by 2, this is the average velocity, and for t from this relation we will get v minus v naught by a. This is the x minus x naught. So then we will have x minus x naught will be equal to, so this is the v naught plus v, or v plus v naught, and v minus v naught over 2a. So again this will turn as v square minus v naught square over 2a, and if we rearrange it, v square minus v naught square will be equal to x minus x naught into 2 here and a here. So this is the fourth equation of motion. So we will write them again. So the first one is v is equal to v naught plus at, and the second one is x minus x naught, or let me say s, is equal to v naught t plus half at square, and then we have x minus x naught is equal to v naught plus v by 2 t, and v square minus v naught square is equal to 2a into x minus x naught. So these were for the acceleration, but if we want to convert them to gravitational subject, and if we deal with gravity, so this will turn into v naught plus v by 2. So all the distance will be replaced by h, and all the acceleration will be replaced by g. So v is equal to v naught plus gt, and h is equal to v naught t plus half gt square, and v square minus v naught square is equal to 2gh. So these are the equations for free fall motion. Here a very sophisticated kind of analogy is used, that what sign should be assigned to the gravitational acceleration, which is 9.8 meter per second square. So usually it depends upon our selection, that if throughout a calculation we nominate the upward motion as positive, so throughout the calculation we have to follow that routine. But if we assign it as negative, then throughout the calculation we have to nominate that kind of thing. But usually the most probable or mostly used approach is that while traveling upward, we assign the g as positive value, and for downward motion we assign the g as negative. So this was for the equations of motion. So what is the practical aspects of it, and how does it applicable in nearly all kind of motions? So we will start with an easy case. So let's suppose you are sitting in a car and you just started in, and you are traveling with 2.5 meter per second square of acceleration, and you travel for 10 seconds. So what will be your velocity at that point after 10 seconds? So we just have to plug in all the values that we know. So we have the equation of motion as this. So we know that as we just started the engine, so the initial velocity is 0, a is 2.5, and t is 10 seconds. So the final velocity will be 25 meter per second. And how far does we go with this time and this acceleration? So here we have another equation that we just calculated from our previous discussion. It is vit plus half at square. So as we know that initially we started our car just from 0, so initial velocity will be 0, so this term get neglected and we left with 2.5 0.2 into 2.5 into 10 square. So here we got the 125 meter of the distance. So we will travel 125 meters of distance, and the final velocity will be 25 meter per second. So this is how it works, and there are also a lot of the cases and a lot of the applications, but we keep it separate for another discussion and for another video that includes purely all the numericals and all the practical kind of examples, along with the intensive formulas and calculations along with. So till that, let me just go through again. So we discussed that we are going to discuss equation of motion, and in kinematics, still Galileo, it was It was considered that all the calculations and all the equations were for celestial bodies, but Galileo was the first who said that by removing all the constants, those equations, as we discussed in Kepler's law and other laws, are also applicable in our real world, in this Earth's frame of reference. So we have four major equations at uniform acceleration which deal with nearly all kind of motions, with one-dimensional, two-dimensional motions, and we calculate them. So the first relation was displacement and average velocity, and we calculated this equation from it. Next one is the velocity and time, and we calculated this equation from it. The position and time relation gives us this equation, and the velocity and displacement relation will ended up here with this relation. Then we change it for the gravitational frame of reference and free fall motion. So these were the equations that we get from it, and we discuss the sign of the gravitational acceleration. So for traveling upward we have positive g, and for traveling downward toward the center of the earth we have negative g, and we discuss a practical kind of example of it. So that's it for today's video. See you tomorrow.